on Slack. There's maybe I'll read the latest question. So is Jonathan in the call? No, maybe I can. Yeah, maybe then like you can get back to him in Slack. So I actually have a question. So maybe I'll just go ahead and ask first. So Xingyu, you mentioned that like there's this herding behavior for drawing the shortest queue. I was wondering like under what conditions does this happen? Like for example, even if you have multiple schedulers, if they have independent Poisson arrivals, then I imagine that would be the same as just having a single stream of arrival and a single scheduler, right? So in that case, is there still going to be any herding behavior?
Okay, so good question. So the herd behavior actually has been observed in a lot of real practical applications. So the motivation is simple. So I think one technical report from Facebook, they show that if you have multiple dispatchers, so in real time, they observe that this performance of this Zhou queue for each schedule or each dispatcher is even worse than random routing. So in some cases, so even if you have some knowledge of the queue length, but if your multiple dispatcher use this kind of Zhou queue policy, the performance is quite poor. So in order to resolve this problem in practice, they often use a power of D. So they often use some randomness because power of D has some randomness. So that one, they show that the power of D is much better in the multiple dispatcher case. But our motivation for this paper is that, okay, instead of use power of D, can we use, because we know that power of D have sampling some measure. So we show that, okay, this kind of local estimates can help us to, to avoid this kind of behavior because these local estimates have introduced another layer of randomness for this kind of dispatch. So I know your point. So you say, okay, well, maybe we have some independent Poisson arrival. So it seems to that we can decouple into an independent system. So in that case, it's not that big for the herd behavior. But I think in practice, people have observed that this herd behavior is very serious for the multiple dispatcher case. Yeah.
I see. Okay, so it's I guess like it would be interesting to see like how this happens like under the theoretical model. So and actually a follow-up question to that, like maybe this is obvious from the talk, but I didn't quite catch that. So does join the shortest queue actually belong to the class LED? So it like it shouldn't, right?
Yeah. So the typical Zhou queue is not in the LED because the typical Zhou queue uses the full information about the true queue length to do the dispatching, but the local Zhou queue is belong to the LED because in the local Zhou queue, each dispatcher only uses his own local estimates to do the dispatching. So each dispatcher may have different estimates of the queue length, so they can do randomly or do differently. But if you use a traditional Zhou queue, it means that all the dispatcher has a true queue length for each queue. So in that case, you will probably join the single shortest queue in that case.
I see. Okay. We have another question from Asek. Maybe Asek, you can just directly ask.
Yeah. Thanks for the talk, Xingyu. What I'm wondering is, so you talked about how randomness can help with this herding behavior. I was wondering whether if one could use asymmetric dispatching policies. So maybe give each dispatcher some subset of the servers that they prefer to send to or something like that to alleviate the herding in a different way.
Yes, good question. That's exactly what we are currently thinking about to generalize. So basically, we gave some subset information to each dispatcher and in the hope that we can further reduce the herd behavior. So good point.
So to clarify, that's a problem you're currently working on, but isn't in this paper?
Yes.
Thanks.
Okay. Other questions?
I have another question. So if I understood correctly, basically, and I still find this surprising. So JSQ with current up-to-date information basically is worse than JSQ with old information.
Yes.
Now, it seems like if you had JSQ with like information from the beginning of time, it would be completely useless. So does this mean that there is some optimal rate of refreshing information, or and if so, do you have any idea what it might be?
Yeah, good question. So basically, as you can see from the paper, that if there is an optimal trade-off between the performance and the message. So if you update the message immediately, so you go back to the normal traditional junction skew. But if you do not update message, so you update very infrequently, your performance can still be very poor. So definitely there is an optimal sweet spot for the updating frequency, but we do not have any idea on it right now. So I think that will be a very interesting future direction to explore. That's my basic intuition for this kind of thing. Yeah.
Thanks.
Okay, so thank you. So maybe due to the time interest, we should move on to the next talk. Sorry, Carrie. So maybe Xingyu will answer your question on Slack.
Yes.